Welcome to the Core Stream. The BYE podcast presents Matrix. Complexity reduced to logic, structured elements.
BYE Matrix, Episode 6, Acoustic Reality and the Architecture of Sound. Welcome back to the BYE Matrix. If you have initiated this sixth transmission, you possess the cognitive bandwidth required for an uncompromising deconstruction of reality. Today, we discard the illusory comfort of silence and physical stillness to interface directly with the invisible architecture of our environment, the physics of sound. We are not here to indulge in simplified acoustic analogies, we are here to interrogate the underlying mathematical scaffolding of wave propagation, psychoacoustic illusions, and the algorithmic manipulation of our auditory perception, from phase cancellation to the deliberate reshaping of reality inside our ear canals. Prepare your neural pathways for a severe paradigm shift. The threshold has been crossed. BYE Matrix is now active. Sound is not an object, but an event, a mechanical disturbance that propagates through a physical medium. At its core, the phenomenon of sound relies on the vibration of matter. When an object vibrates, it displaces the adjacent molecules of the medium, typically air, though the same principles apply to solids and liquids, creating a chain reaction of kinetic energy. This energy travels as a longitudinal wave, where the particles of the medium oscillate parallel to the direction of the wave's travel. This movement manifests as alternating zones of high pressure, known as compressions, and low pressure, known as rarefactions. To master the language of audio and acoustics, we must first dissect the fundamental parameters that govern these pressure waves: frequency, amplitude, phase, and the mechanics of propagation. Frequency refers to the rate at which a wave completes a full cycle of compression and rarefaction within a specific time frame. In scientific terms, it is measured in Hz/Hz, where 1 Hz equals 1 cycle per second. From a psychoacoustic perspective, our brains interpret frequency as pitch. A high-frequency wave, such as the trill of a piccolo or the hiss of sibilants, features tightly packed cycles, whereas a low-frequency wave, like the rumble of thunder or the thrum of a bass guitar, has elongated cycles. The human ear can theoretically perceive a broad spectrum of frequencies, typically spanning from 20 Hz to 20,000 Hz, 20 kHz. As frequency increases, the wavelength, the physical distance between two consecutive peaks of a wave, shortens. Conversely, low frequencies possess vast wavelengths. A 40 Hz tone, for instance, has a wavelength of roughly 8.5 meters in air, a physical reality that poses immense challenges for acoustic treatment. Amplitude is the measure of the physical displacement of particles within the medium, representing the magnitude of the pressure variation from the static atmospheric pressure. In simpler terms, it is the height of the wave crest. The greater the energy injected into the initial vibration, the more violent the compression of air molecules, and the higher the amplitude. We quantify this acoustic pressure using the decibel, dB, scale, a logarithmic ratio that reflects the human ear's nonlinear perception of volume. While amplitude is the objective, measurable physical quantity, loudness is the subjective psychological sensation. Because our ears are more sensitive to mid-range frequencies, the band where human speech resides, than to extreme lows or highs, two waves with identical physical amplitude but different frequencies will not be perceived as equally loud. Phase describes the specific point in time that a wave has reached within its cyclical journey, measured in degrees from 0 degrees to 360 degrees. When two or more sound waves meet in the same space, they do not simply bounce off one another, instead, they combine through a process called superposition. This interaction is entirely dependent on their relative phase relationships. With constructive interference, if two identical waves are perfectly in phase, aligned at 0 degrees, their peaks and troughs coincide exactly. The energies reinforce one another, resulting in a combined wave with double the amplitude, plus 6 dB. With destructive interference, if one wave is shifted by 180 degrees relative to the other, they are perfectly out of phase. The peak of the first wave meets the trough of the second with equal force. The pressure changes cancel each other out entirely, resulting in complete silence. In real-world environments, total cancellation is rare, but phase interference frequently causes comb filtering, a phenomenon where certain frequencies are boosted and others are scooped out, severely coloring the tonal quality of the sound. Sound cannot travel through a vacuum. It is entirely dependent on the elasticity and density of the medium it inhabits. The speed of sound is not fixed, it varies according to the material through which it passes. In air at a room temperature of 20 degrees Celsius, sound travels at roughly 343 meters per second. However, because molecules are more tightly packed in liquids and solids, kinetic energy is transferred much more rapidly. Sound travels roughly 4 times faster in water and more than 15 times faster in steel. Furthermore, environmental factors such as temperature, humidity, and barometric pressure alter air density, thereby subtly shifting the speed of sound and affecting how audio waves behave in open spaces. When sound is unleashed within an enclosed space, its journey becomes infinitely more complex. It no longer behaves as a pure, unfettered wave in a free field. Instead, it strikes boundaries, walls, ceilings, floors, and furniture, and its energy is fundamentally reshaped by these encounters. The science of environmental acoustics explores how these physical structures alter the sonic landscape. When a sound source ceases, the sound does not vanish instantaneously. It undergoes a dense series of reflections that bounce off every available surface, gradually decaying over time. This lingering wash of sound is reverberation. The timeline of a reverberant field can be split into 3 distinct phases. Direct sound is the initial, unaltered wave that travels in a straight line from the source to the listener's ears or microphone without striking any surface. This provides the cleanest tonal information. Early reflections are the first few waves that bounce off a single surface, like a nearby wall or the ceiling, before reaching the listener. Arriving within roughly 50 milliseconds of the direct sound, these reflections provide vital cues about the size of the room. Late reverberation, or the reverb tail, occurs as the reflections continue to bounce off multiple surfaces. They multiply exponentially, losing their individual identity and blending into a dense, chaotic cloud of decaying sound. Acousticians measure this decay using RT60, reverberation time 60, which defines the time it takes for the sound pressure level to drop by 60 decibels after the original sound source has stopped. A cavernous cathedral might have an RT60 of several seconds, creating a lush but muddy wash, whereas a heavily treated recording studio aims for a tight, controlled RT60 of a fraction of a second to ensure clarity. Not all surfaces treat sound waves equally. When a wave hits a boundary, some of its energy is reflected back into the room, some is transmitted through the structure, and some is absorbed, converted into microscopic amounts of heat via friction. The efficiency of a material's ability to absorb sound is rated by its absorption coefficient alpha, which ranges from 0.0 for perfect reflection to 1.0 for perfect absorption. High absorption, alpha near 0.9, is found in porous materials like open-cell acoustic foam, heavy velvet curtains, or dense rockwool panels. The air molecules penetrate the material, rubbing against the fibers and losing their kinetic energy as heat. These materials are highly effective at taming mid- and high-frequency reflections. Low absorption, alpha near 0.05, is found in hard, non-porous surfaces like polished concrete, plate glass, or solid brick. These boundaries offer virtually no friction, reflecting almost all the acoustic energy back into the room, causing flutter echoes and harsh acoustic environments. If absorption is the elimination of acoustic energy, diffusion is its redistribution. When a sound wave strikes a flat, hard wall, it bounces off specularly, meaning the angle of reflection equals the angle of incidence, much like a billiard ball hitting a cushion or light striking a mirror. This can create harsh, concentrated reflections known as hotspots. A diffuser is an acoustical element with an intentionally irregular, jagged surface profile, often calculated using mathematical sequences, such as quadratic residue diffusers. When a wave hits a diffuser, the energy is scattered evenly in a multidirectional pattern across both time and space. The total acoustic energy remains within the room, but the distinct, problematic reflections are broken up, preserving a sense of spaciousness and liveness without the flutter echoes. The most insidious enemy of accurate monitoring in any room is the room mode. Room modes are natural resonance frequencies dictated entirely by the physical dimensions of the space. When the distance between 2 parallel walls matches a specific wavelength, or a multiple of it, the reflected waves trap themselves, continuously bouncing back and forth in perfect alignment with incoming waves. This creates a standing wave. Unlike a normal wave that appears to travel through space, a standing wave oscillates in a fixed position. This results in permanent geographical anomalies within the room. Nodes are points in space where the direct and reflected waves are out of phase, causing severe cancellation. If you sit in a node, you will experience a dramatic drop-off, sometimes a complete absence, of that specific low-end frequency. Antinodes are points where the waves are perfectly in phase, causing massive acoustic buildup. In an antinode, which is frequently found in the corners of a room, the bass will sound bloated, boomy, and wildly exaggerated. Because low frequencies have such long wavelengths, room modes primarily wreak havoc in the low-end spectrum, typically below 300 Hz. Taming these modes requires massive bass traps capable of absorbing the immense kinetic energy of low-frequency pressure waves. Acoustics deals with the physical pressure waves in the air. Psychoacoustics deals with what happens once those waves pass through the ear canal and are translated into electrochemical signals by the auditory nerve. Our brains are incredibly sophisticated organic computers, capable of dissecting minute discrepancies in sound waves to reconstruct a highly accurate, three-dimensional mental map of our surroundings. In reality, stereo does not exist in nature. We have only two ears, yet we perceive a fully immersive, 3D world. In audio production, the stereophonic illusion relies on fooling the brain into perceiving a continuous soundstage between two speakers. By manipulating the relative volume and timing of a signal sent to the left and right channels, engineers can trick the auditory system into localizing a sound at any phantom position between the speakers, even though no physical sound source exists there. To pinpoint exactly where a sound originates along the horizontal plane, the azimuth, the brain relies on two primary mechanisms: interaural time difference, ITD, and interaural level difference, ILD. Interaural time difference occurs if an acoustic event happens to your left. The sound wave must travel a slightly shorter distance to reach your left ear than your right ear. The human head acts as a physical obstacle, creating a tiny time delay, often a matter of mere microseconds, between the two ears. The brain detects this infinitesimal arrival time discrepancy and instantly determines the angle of the sound source. ITD is the dominant localization cue for low-frequency sounds, below 1.5 kHz, where the wavelengths are larger than the diameter of the head, allowing the wave to bend easily around the skull. Interaural level difference applies to higher frequencies, above 1.5 kHz, where the wavelength is shorter than the width of the human head. Consequently, the head acts as an acoustic barrier, casting an acoustic shadow over the far ear. A sound originating from the left will strike the left ear directly, but will be significantly attenuated and quieter by the time it diffuses around the skull to reach the right ear. This difference in amplitude or volume level between the two ears is the primary cue the brain uses to localize high-pitched sounds. How do we tell if a sound is above us, behind us, or below us if the ITD and ILD are identical? This is where the complex, unique architecture of our outer ear comes into play. The folds of the pinna, the external ear, the shape of the ear canal, and even the contours of our shoulders and torso act as an intricate acoustic filter. As sound waves hit these physical structures, they undergo subtle, frequency-dependent reflections and phase cancellations before entering the ear canal. This filtering effect changes drastically depending on whether a sound comes from above, below, ahead, or behind. The brain learns this filtering profile from infancy, using it as a sonic fingerprint to decode elevation and front-to-back orientation. In modern audio engineering, this complex acoustic transfer function is captured mathematically as the head-related transfer function, HRTF. By applying HRTF filters to standard audio tracks, engineers can create stunningly convincing 3D spatial audio experiences through standard headphones. Autonomous sensory meridian response, ASMR, is often described colloquially as a brain tingle, but from a psychoacoustic and neurological perspective, it represents a highly specific, static-like tingling sensation that originates at the vertex of the cranium, cascading down the line of the nuchal ligament and spreading across the shoulders. This phenomenon is mediated by peripheral somatosensory pathways, triggered by precise, low-velocity acoustic stimuli. These triggers, ranging from crisp, low-amplitude sibilants and fricatives in whispered speech to the rhythmic, high-frequency transients of fingernails tapping on polyhedral surfaces, exploit our evolutionary biology. They mimic the sonic signature of intimate, non-threatening social grooming, which induces a state of profound parasympathetic dominance, characterized by a reduced heart rate and an increase in skin conductance levels. To successfully engineer this psychological state in an industrial or studio setting, traditional stereophonic recording techniques are utterly inadequate. Standard stereo panning merely alters the relative amplitude between the left and right channels, failing to replicate how human anatomy filters sound. To deceive the brain into perceiving a true, physical presence, sound engineers deploy binaural recording technology. At the heart of this method lies the Kunstkopf, or dummy head microphone. This is a precise acoustic replica of a human head, complete with anatomically accurate pinnae, the external ear flaps, auditory canals, and internal acoustic impedance that mirrors human flesh and bone. Microphones are embedded deep within the simulated canals, precisely where the tympanic membranes would be. When a sound wave hits the dummy head, it undergoes the exact physical transformations that a real listener would experience. These transformations are mathematically defined as the head-related transfer function, HRTF. The HRTF is dictated by three primary acoustic variables. Interaural time difference is the minute delay, measured in microseconds, it takes for a sound wave to reach the farther ear compared to the closer one, allowing the brain to calculate horizontal azimuth. Interaural level difference is the acoustic shadow cast by the mass of the skull, which attenuates high-frequency sounds reaching the far ear. Pinna filtering involves the complex reflections and phase cancellations caused by the unique folds of the outer ear, which provide the vital spectral cues required to distinguish whether a sound originates from above, below, ahead, or behind. When these binaural tracks are played back through headphones, the listener's loudspeakers are decoupled from the room acoustics. The recorded HRTF is delivered directly to the eardrums, completely bypassing the listener's actual surroundings and tricking the central nervous system into mapping a vivid, three-dimensional auditory space that feels breathtakingly real. The deception of the human auditory cortex deepens when we look at the neurological manipulation known as binaural beats. Unlike standard acoustic beats, which occur when two slightly different frequencies combine physically in the air to create a pulsating wave, binaural beats are an entirely central nervous system illusion. They are generated within the superior olivary complex, the brainstem structure responsible for sound localization. If a continuous tone of 400 Hz is delivered to the left ear, and a synchronous tone of 410 Hz is delivered to the right ear, the air outside remains completely still, no physical interference takes place. However, as the neural impulses travel up the auditory pathways, the superior olivary complex attempts to reconcile the phase discrepancy between the two signals. The result is a perceived, internal third frequency of 10 Hz, the arithmetic difference between the two stimuli. This subjective cortical fluctuation is exploited to encourage neural entrainment. Electroencephalography studies demonstrate that prolonged exposure to these phantom frequencies can coax dominant brainwave activity to shift toward specific bands. For instance, a 10 Hz binaural beat targets the alpha band, associated with calm, alert wakefulness, whilst lower frequencies in the delta, 0.5 to 4 Hz, or theta, 4 to 8 Hz, ranges are engineered to induce deep sleep or meditative states. Simultaneously, industrial sound design relies on sophisticated digital signal processing, DSP, to create the illusion of 3D spatialization over standard stereo fields. By utilizing dynamic crosstalk cancellation algorithms and real-time HRTF convolution, engineers can phase shift and delay audio packets on the fly. This manipulates our perception of distance, velocity, and elevation, allowing a sound source to seemingly orbit the listener's head within a virtual matrix, long before it ever enters the physical room. Acoustic manipulation has long escaped the confines of the laboratory and laboratory testing. It is now deeply integrated into commercial manufacturing, infrastructure, and consumer psychology. In the premium automotive sector, sound is not merely a byproduct of mechanical operation, it is a meticulously engineered asset used to signal quality, luxury, and brand identity. This is most obvious in the design of the door closure sound. The specific, authoritative thud of a luxury car door closing is entirely artificial. A raw, unengineered door closure produces a harsh, metallic clang caused by high-frequency vibrations in the sheet metal and the latch mechanism. To transform this into a premium acoustic signature, automotive manufacturers use advanced structural dampening. They apply elastomeric compounds inside the door panels to absorb high frequencies and tune the rubber seals around the frame to act as low-pass filters. The goal is to isolate a low-frequency, high-amplitude acoustic pulse, typically centered between 50 Hz and 100 Hz, with a rapid, clean decay. This specific acoustic profile signals structural solidity, safety, and prestige to the consumer subconscious. With the advent of electric vehicles, EVs, automotive sound engineers faced an entirely new challenge. Because electric powertrains are inherently silent at low speeds, they present a significant hazard to pedestrians, whilst denying the driver the expected sensory feedback of acceleration. Under international regulations, manufacturers must now integrate acoustic vehicle alerting systems, AVAS. Rather than simply replicating the rumble of a traditional internal combustion engine, brands engineer bespoke synthetic soundscapes. Using real-time telemetry, such as throttle position, torque demand, and road speed, onboard DSP engines synthesize complex harmonic arrays. These sounds are designed to scale smoothly in pitch and intensity, providing an organic sense of acceleration while forging a distinctive sonic identity for the vehicle. Active noise cancellation represents one of the most elegant applications of real-time destructive interference. The fundamental physics governing ANC is the principle of superposition. When two acoustic waves of identical frequency and amplitude meet, their net pressure is determined by their phase relationship. If they are perfectly aligned, they reinforce one another. If they are exactly 180 degrees out of phase, they cancel each other out completely. Inside an ANC headphone or a premium vehicle cabin, miniature electret or MEMS microphones continuously sample the ambient environment. This analog noise signal is converted to digital format and fed into a high-speed DSP chip. The processor runs an adaptive filtering algorithm, typically a least mean squares algorithm, to predict the incoming acoustic waveform. The DSP then generates a matching anti-noise wave. This waveform is identical in frequency and amplitude but inverted by exactly 180 degrees. This anti-noise signal is amplified and pumped through the headphone drivers or cabin speakers just as the original ambient wave arrives. The crest of the intrusive sound wave meets the trough of the synthesized anti-noise wave, resulting in a dramatic reduction in ambient sound pressure. ANC is highly effective at neutralizing continuous, low-frequency sounds, such as the drone of an aircraft engine or the roar of road surface friction, because these predictable waves give the processor enough time to calculate and inject the inverted signal. However, sharp, transient sounds, such as a sudden shout or a car horn, remain difficult to cancel entirely due to the processing latency inherent in digital systems. Within commercial spaces, sound is weaponized to subtly alter consumer behavior, manage anxiety, and optimize revenue streams without the consumer ever realizing they are being influenced. Retail and supermarket giants routinely employ specific background music tempos to manipulate dwell time, the duration a shopper spends browsing the aisles. Research shows that slow-tempo music, under 72 beats per minute, directly influences a shopper's pace. It triggers a subconscious deceleration in gait, causing consumers to move slowly through commercial displays, which increases impulse purchases by up to 38%. Conversely, fast casual restaurants use high-tempo, high-amplitude music during peak hours to accelerate queuing rates and table turnover, maximizing profits during tight service windows. Beyond tempo, corporate sound designers manipulate specific frequencies to alter mood and manage stress. In high-anxiety environments, such as airport security lines or dental waiting rooms, soundscapes are engineered to emit harsh, high-frequency transients. Instead, they focus on low-pass filtered, ambient textures and pink noise profiles, which decrease cortisol levels and lower blood pressure. This ties directly into sonic branding, the creation of brief, highly memorable acoustic hooks, or audio mnemonics, that instantly evoke a brand's identity. These short sequences are mathematically tuned to trigger a dopaminergic response, cementing a consumer's emotional connection to a brand within a fraction of a second. Mixing is the defining bridge between raw performance and a polished, commercial record. It is not merely a technical exercise in balancing levels, it is the art of sculpting three-dimensional space, managing psychoacoustic perception, and carving out distinct sonic real estate for every element within a multi-track session. A masterful mix requires a British sound engineer's mindset, a blend of surgical precision, creative intuition, and a deep appreciation for the subtle, non-linear characteristics of analog hardware. To achieve a mix that sounds expansive, cohesive, and impactful, you must master the core pillars of audio processing, frequency manipulation, dynamic control, harmonic enrichment, and spatial placement. This technical lab dissects these cardinal tools, providing the definitive principles required to transform a cluttered arrangement into a breathing, unified masterpiece. Equalization is the fundamental tool for managing the frequency spectrum. A professional mix relies on a dual-stage approach to EQ, first, fixing structural problems within individual tracks, and second, enhancing the emotional and aesthetic qualities of the sound. Before attempting to make a track sound beautiful, it must first be made clean. Surgical EQ is primarily corrective and is best executed using transparent, high-precision digital parametric equalizers. One of the most common pitfalls in a mix is the accumulation of low-end rumble and sub-bass buildup from non-bass instruments, such as acoustic guitars, vocals, and hi-hats. While this low-frequency energy may not be audible in isolation, it consumes massive amounts of headroom on your master bus and causes the low end of your mix to become muddy and indistinct. Implementing a high-pass filter on non-bass tracks, gently rolling off frequencies below 80 Hz or 100 Hz, cleans up the low-end anchor, leaving the sub-bass territory exclusively for the kick drum and the bass guitar. Every recording environment and instrument possesses inherent resonant peaks that can sound harsh, boxy, or ringing. To eliminate these, engineers employ the sweep technique. Use a parametric EQ band with a very narrow, sharp bandwidth, a high Q factor, boost the gain significantly, plus 10 dB to plus 15 dB, and slowly sweep through the frequency spectrum while the track plays. When you hit a frequency that suddenly rings painfully or sounds excessively muddy, you have located a problem resonance. Pull the gain down into a sharp cut of 3 to 6 dB to attenuate that specific frequency without affecting the surrounding musical content. Once the problem frequencies are removed, you can pivot to creative enhancement. This is where the distinct character of legendary British-style analog console EQs, such as classic SSL, Neve, or Trident desks, shines. Unlike transparent digital EQs, these analog models introduce subtle, pleasing phase shifts and musical curves that flatter the audio. Broad, gentle boosts in the low mids, around 100 Hz to 250 Hz, using an analog-modeled shelving EQ can instantly inject weight and body into a thin vocal or a snare drum. The mid-range, 500 Hz to 3 kHz, is where the human ear is most sensitive and where mixes frequently become cluttered. Instead of boosting the mid-range of every instrument to make it cut through, use complementary EQ. If the lead vocal needs prominence at 1.5 kHz, cut that exact frequency by 1.5 dB on the electric guitars and keyboards. This creates a bespoke sonic pocket for the vocal to sit in naturally. To make a mix sound expensive and polished, focus on the top end, 10 kHz and above. A subtle, wide high shelf boost on vocals, drum overheads, or acoustic guitars creates a sense of expensive boutique openness and clarity that lifts the entire track without making it sound harsh or sibilant. If EQ manages the horizontal frequency spectrum, compression governs the vertical dynamic range. A compressor attenuates the loudest parts of an audio signal, reducing the distance between the quietest and loudest passages to ensure consistency and impact. To control a compressor effectively, you must understand how its interactive controls alter the envelope of a sound. The threshold is the level in decibels above which the compressor begins to reduce the volume. Anything below this level passes through unaffected. The ratio determines how much gain reduction is applied once the signal crosses the threshold. A 4:1 ratio means that for every 4 dB the input signal exceeds the threshold, only 1 dB is allowed out. Higher ratios, 8:1 and above, act more aggressively, while lower ratios, 1.5:1 or 2:1, offer gentle, transparent control. The attack time is the speed at which the compressor clamps down on the audio once it crosses the threshold. A fast attack time, measured in microseconds or a few milliseconds, catches transients instantly, which is ideal for controlling a peaky vocal. However, on drums, a fast attack can crush the initial smack of the stick hit, making them sound flat. A slower attack allows the initial transient to pass through untouched before compressing the tail, retaining punch. The release time is how quickly the compressor returns to unity gain after the signal drops below the threshold. If the release is too fast, the audio can pump unnaturally. If it is too slow, the compressor never recovers, permanently attenuating the quiet parts of the performance. The goal is often to set the release time in time with the tempo of the music, allowing the gain reduction fader or needle to dance rhythmically with the track. Because compression reduces the peak levels of an audio signal, the overall perceived volume drops. Make-up gain is applied at the output stage to bring the compressed audio back up to a competitive level, effectively lifting the quieter details and making the entire performance sound denser and more consistent. To prevent a mix from sounding like a loose collection of individual tracks, engineers insert a compressor across the master bus, the main stereo output. Often utilizing a VCA-style compressor, like the legendary SSL master bus compressor, this technique uses a low ratio, 1.5:1 or 2:1, a slow attack, and an auto-release setting. The goal is minimal gain reduction, only 1 to 2 dB of movement. This subtle compression acts as a sonic adhesive, gently binding the disparate tracks together so they react as a singular, cohesive piece of music. Parallel compression, often called the New York trick, allows you to achieve the best of both worlds, extreme dynamic excitement and intact, organic transients. You duplicate a track, such as the drum bus or lead vocal, or send it via an auxiliary bus to a dedicated compressor channel. On this auxiliary parallel track, you apply brutal, heavy compression, a high ratio, fast attack, fast release, and deep gain reduction to smash the audio, bringing out intense room energy and massive weight. You then subtly blend this smashed, aggressive parallel track underneath the clean, uncompressed original track using the fader. The original track provides the clean, sharp transients, while the parallel track provides a thick, powerful foundation underneath. In the purely digital domain of modern DAWs, audio can occasionally sound sterile, cold, and overly clinical. This is because digital recording is linear and mathematically perfect. Analog hardware, conversely, is beautifully imperfect. When valves, tape machines, and transformers are driven with audio signals, they introduce subtle, non-linear distortion known as harmonic saturation. Saturation generates entirely new frequencies that are mathematically related to the original fundamental note. Tubes generate predominantly second-order even harmonics. These harmonics sound warm, thick, and incredibly pleasing to the human ear. Adding valve saturation to a bass guitar or a lead vocal introduces a rich, velvety low-mid characteristic that makes the sound feel close, intimate, and expensive. Tape machines introduce odd-order harmonics along with a unique phenomenon known as tape high-frequency roll-off and compression. As a signal hits tape hard, the high frequencies naturally smooth out, softening any digital harshness, while the low end undergoes a subtle bump, the tape head bump. Running a full mix or a drum group through a high-quality tape emulation plugin glues the elements together, tames brittle high frequencies, and delivers a classic, vintage rock and roll vibe. Saturation is a powerful tool for psychoacoustics. If a bass guitar is lost when a mix is played back on small consumer speakers, like smartphones or laptops, because those devices cannot reproduce sub-bass frequencies, do not boost the low-end EQ. Instead, apply harmonic saturation to the bass. The newly generated upper harmonic overtones will cut through the mid-range spectrum, allowing the listener's brain to perceive the presence of the bass guitar even on speakers that physically cannot reproduce the fundamental low notes. A pristine mix cannot exist purely in a flat, two-dimensional landscape. To captivate a listener, a mix must exhibit depth, establishing a front-to-back perspective where some elements feel close enough to touch, while others recede gracefully into the background. These spatial dimensions are governed by time-based effects, delay and reverberation. Delay takes an audio signal and plays it back a specified amount of time later, creating distinct echoes. It is often preferred over reverb when an engineer wants to create space without cluttering the frequency spectrum. Slapback delay involves a single, short echo with a delay time between 40 milliseconds and 120 milliseconds and zero feedback. Popularized in 1950s rockabilly and 1980s pop, slapback delay gives a vocal or electric guitar an instant sense of space and attitude without washing out the performance. It makes a vocal sound wider and thicker without the listener explicitly noticing a distinct delay effect. Ping-pong delay is a stereo delay effect where the echoes alternate back and forth between the left and right speakers. Tied to the tempo of the track, such as dotted eighth notes or quarter notes, ping-pong delays add exciting, cinematic horizontal movement to synth leads, backing vocals, or guitar solos. Reverberation consists of thousands of dense, overlapping echoes that simulate the acoustic reflections of a physical space. By manipulating the decay time and pre-delay, you can position any instrument precisely on the virtual stage. Pre-delay is the amount of time between the initial dry sound and the onset of the reverb reflections. If you set a pre-delay of 0 milliseconds, the reverb explodes instantly alongside the sound, washing it out and pushing it directly to the back of the mix. By dialing in a pre-delay of 20 milliseconds to 40 milliseconds, you allow the clean, dry transient of a lead vocal or snare drum to articulate clearly at the front of the stage before the ambient reverb tail blooms behind it. This maintains pristine definition while still providing a lush sense of space. Mechanical plate reverbs, which historically used a vibrating sheet of metal, are bright, dense, and smooth. They do not sound like a real room, but they are incredibly flattering on lead vocals and snare drums, adding a brilliant, glossy sheen. Characterized by a quirky, metallic sound, spring reverbs are synonymous with surf rock, vintage guitar amplifiers, and dub reggae. They introduce character, grit, and an instantly recognizable retro vibe. Rooms and chambers create short, tight acoustic environments with 0.5 to 1.2 seconds of decay. They are perfect for gluing a dryly recorded drum kit together, making it sound as though the band recorded simultaneously in a world-class, acoustic studio space. Halls simulate large, majestic spaces with long decay times of 2.0 seconds and beyond. Halls replicate cathedrals or concert arenas, making orchestral arrangements, ambient pads, or emotional ballad vocals sound epic, deep, and larger than life. However, they must be used sparingly to avoid drowning the entire mix in a washed-out, indistinct mud bath. The secret of the technical lab lies in the interaction of these tools. EQ clears the space, compression solidifies the performance, saturation injects character, and time-based effects construct the environment. By approaching each mix with intention and implementing these definitive British engineering principles, you will consistently deliver mixes that are powerful, deep, and sonically immaculate. You have spent hours hunkered down in your studio, meticulous and unyielding, tweaking the compression on the snare and carving out a precise pocket for the bass. Through your studio monitors, the track sounds sublime, punchy, transparent, and perfectly balanced. Confident in your masterpiece, you bounce the file, transfer it to your phone, and head out for a drive. But the moment the track kicks in through the car stereo, your jaw drops. The sub-bass is a muddy, overwhelming roar that completely swallows the vocals, the guitars sound thin and grating, and the snare has lost all its authority. Welcome to the harsh reality of mix translation. This phenomenon describes a mix's ability to maintain its structural integrity, balance, and emotional impact across an infinite variety of playback systems. The fundamental conundrum of modern audio engineering is that we do not mix for ourselves, we mix for the world. And the world does not listen in acoustically treated rooms on flat response monitors. They listen on cheap earbuds during their morning commute, through tinny laptop speakers on their laps, or via hyped consumer hi-fi systems in their living rooms. Bridging this chasm requires an intimate understanding of playback profiles and the physical constraints of transducer technology. The ultimate test of a great mix is not how pristine it sounds in the room where it was born, but how well it translates to environments that are hostile to good audio. A track is a chameleon, it must adapt to different frequency responses, acoustic spaces, and hardware limitations without losing its core identity. When a mix falls apart on consumer gear, it is usually because the engineer fell into the trap of mixing for their specific room and speakers, rather than accounting for the translation curve. For instance, if your mixing space has an untreated acoustic node that naturally cancels out frequencies around 100 Hz, you will instinctively boost that region in your mix to compensate. When that same track is played back in a car, an environment notorious for its boomy, unpredictable low-end resonance, that 100 Hz boost becomes an unbearable, muddy mess. Achieving translation means making compromises. It means ensuring that the bassline has enough harmonic content in the mid-range, the 700 Hz to 1.5 kHz zone, so that it remains audible on a smartphone speaker that cannot physically reproduce anything below 200 Hz. It means controlling the harshness around 3 kHz to 5 kHz so it does not pierce the listener's eardrums when played through cheap, poorly damped earbuds. To conquer the hardware divide, we must analyze the two radically opposed philosophies of transducer design, the clinical truth of the studio monitor versus the flattering deception of consumer audio. Professional studio monitors are engineered with one overriding purpose: absolute, unvarnished neutrality. They aim for a completely flat frequency response, meaning they do not inherently boost or cut any part of the audio spectrum. If a recording is muddy, the monitors will sound muddy. If it is harsh, they will sound harsh. They act as an acoustic microscope, exposing flaws so that the engineer can fix them. However, a flat response monitor is only as good as the room it sits in. Without extensive acoustic treatment, such as bass traps, broadband absorbers, and diffusers, the boundaries of the room will create standing waves and phase cancellations that utterly destroy the monitor's flat profile. Furthermore, professional monitors require clean, robust amplification, whether internal in active designs or via high-end external power amps connected to the mains, to ensure that transient peaks are reproduced without a hint of distortion or clipping. In stark contrast, consumer audio gear, ranging from commercial hi-fi systems to Bluetooth speakers and standard car stereos, is designed to make everything sound instantly exciting, warm, and polished. To achieve this, manufacturers almost universally employ a V-shaped or scooped frequency response curve. In a V-shaped profile, the low end is heavily hyped to provide artificial warmth and thump, while the top end is boosted to give an illusion of clarity and air. Crucially, the mid-range is scooped out. Manufacturers do this because the mid-range is where human hearing is most sensitive, and it is also where acoustic clutter lives, nasal vocal frequencies, harsh guitar resonance, and boxy snare drums. By scooping the mids, consumer gear hides these problematic frequencies, making poor recordings sound acceptable. For the mixing engineer, this is a minefield. If you mix on a system with a V-shaped curve, you will naturally pull down your bass and treble because they sound too loud, and you will push your mids up to compensate for the scoop. When your mix is played back on a flat or mid-forward system, it will sound incredibly mid-heavy, dull, and completely devoid of low-end power. With a massive portion of the global audience now consuming audio exclusively through headphones and earphones, collectively referred to as cans and buds, an engineer must understand the mechanical and acoustic forces at play when drivers are placed directly against or inside the human ear. When it comes to over-ear headphones, the architectural split between open-back and closed-back designs fundamentally alters the listening experience. Closed-back headphones feature solid ear cups that completely seal the driver from the outside world. This design offers excellent acoustic isolation, preventing ambient noise from leaking in and stopping the audio from bleeding out into the room, which is essential for tracking vocals in front of a live microphone. However, the trapped air inside the ear cup creates internal reflections and pressure buildup. This inevitably results in a less accurate, often hyped low-end response and a narrower, more claustrophobic soundstage. Open-back headphones have ear cups that are perforated or covered with a mesh grill, allowing air and sound to pass freely through the back of the driver. This elimination of internal pressure allows the diaphragm to move with incredible precision, resulting in an exceptionally flat, natural bass response and an expansive, lifelike soundstage that mimics listening to a pair of high-end monitors in a perfect room. The trade-off is zero isolation. They bleed sound profusely and are completely unsuited for noisy environments or tracking sessions. Headphone performance is heavily dictated by impedance, measured in ohms. Low impedance cans, typically below 50 ohms, are designed for mobile devices, laptops, and consumer gear. They require very little voltage to reach high volumes, making them highly efficient but often prone to a lower damping factor, which can compromise bass control. High-impedance cans, ranging from 250 ohms to 600 ohms, such as those found in professional studios, require dedicated, high-voltage headphone amplifiers to drive them properly. When adequately powered, high-impedance voice coils offer far greater precision, reducing distortion and delivering an incredibly detailed, tight transient response across the entire frequency spectrum. Attempting to plug high-impedance cans directly into a standard smartphone will result in a quiet, thin, and completely gutless sound. When we listen to loudspeakers in a room, the sound changes before it reaches our eardrums. It reflects off walls, diffracts around our shoulders, and interacts with the shape of our outer ear, the pinna. This complex acoustic transformation is known as the head-related transfer function, HRTF. Because headphones bypass the room and the outer ear entirely, firing sound straight down the ear canal, a truly flat measurement headphone driver would actually sound incredibly bright, thin, and unnatural to the human brain. To solve this, researchers developed the Harman target curve. The Harman target is a specific, scientifically derived frequency response curve that alters the headphone's output to replicate the acoustic response of a pair of perfectly flat studio monitors playing inside a pristine, acoustically treated listening room. It features a distinct boost in the sub-bass to compensate for the lack of physical, chest-thumping bass impact you get from real speakers, and a precise correction peak around 3 kHz to mimic the natural resonance of the human ear canal. Understanding how your mixing headphones conform to or depart from the Harman target is vital. If your cans lack the necessary correction peaks, you will make incorrect mixing decisions in the critical mid-range and high-frequency zones, ruining your track's chances of proper translation. To achieve a mix that stands up on the mains of a club, the car stereo on the motorway, and cheap plastic earbuds alike, you must learn to reference constantly. Use your flat response studio monitors to build the foundation and catch structural errors. Switch to open-back cans to inspect fine details and spatial imaging without room interference. Finally, check your work on low-end consumer systems to ensure your mid-range choices hold the track together when the bass and treble are artificially manipulated. Only by checking your mix through these various hardware profiles can you ensure your track translates seamlessly, delivering the exact same emotional gut punch to every single listener, regardless of the gear they use. The landscape of personal audio has undergone a profound structural transformation over the past decade. We have moved decisively away from passive acoustic drivers, which relied entirely on the raw electrical signal sent down a copper wire from a dedicated amplifier, towards wireless, highly integrated, computational audio powerhouses. Modern wireless earbuds and mobile headphones are no longer mere speakers strapped to one's ears. They are microcomputing platforms equipped with dedicated silicon, independent power management, and sophisticated sensor arrays. At the heart of this shift is the miniaturization of the hardware stack. Within the cramped housing of a contemporary wireless earbud, manufacturers now integrate ultra-low-power system-on-chip architectures, high-performance digital-to-analog converters, multiple micro-electromechanical systems microphones, and dedicated neural processing units running bespoke firmware. This hardware evolution fundamentally alters the relationship between the mobile phone and the playback device. In a traditional setup, the smartphone performed all the heavy lifting, outputting a finished analog wave. Today, the smartphone merely transmits compressed digital data streams via Bluetooth. The true acoustic staging, decoding, and environmental adaptation occur locally within the earbud itself. This decentralization of processing power allows for what is known as computational audio. Because the device sits directly inside or over the ear canal, it can use its internal, inward-facing microphones to measure the acoustic properties of the user's specific physical anatomy. It then alters the sound signature on the fly to compensate for a poor seal, the shape of the concha, or the unique resonance of the listener's ear canal. The result is a shift from generic acoustic reproduction to highly individualized, contextual sound delivery. The true magic of modern mobile audio architecture lies in its ability to execute complex digital signal processing operations with near-zero latency. For an audio experience to feel natural and uninhibited, especially when monitoring one's own voice or interacting with the environment, the round-trip latency of the processing loop must remain well below 10 milliseconds. Within this incredibly tight window, modern onboard algorithms execute millions of calculations to tailor the audio stream to both the surrounding environment and the biological profile of the listener. When an audio signal is decoded on the earphone's local chip, it passes through a multiband DSP pipeline. This pipeline does not treat the audio as a single, uniform wave. Instead, it splits the signal into dozens of discrete frequency bands. Each band can be manipulated independently based on telemetry data gathered by the external and internal MEMS microphones. Furthermore, this technology has paved the way for sophisticated biological hearing adaptation. Instead of applying a generic equalization curve, modern mobile operating systems and earphone applications allow users to input personal audiograms or undergo interactive, in-ear hearing tests. The onboard DSP then uses these biological blueprints to construct a permanent compensation curve. If a user exhibits a specific drop-off in high-frequency perception due to age or noise-induced hearing loss, the algorithm dynamically boosts those specific frequencies before the sound ever hits the eardrum. This real-time correction effectively counteracts biological deficiencies, restoring a full-spectrum auditory experience without requiring clumsy, external medical hardware. To achieve genuine accessibility and effortless legibility in everyday scenarios, consumer audio tech has adopted processing techniques originally developed for high-end studio recording and clinical audiology. These techniques fundamentally alter the original studio mix of music, podcasts, or phone calls, prioritizing structural clarity and speech intelligibility above absolute purist fidelity. In the context of acoustic engineering, the dynamic range represents the delta between the quietest and the loudest parts of an audio signal. While a wide dynamic range is desirable in a quiet listening room or a cinema, it presents a massive accessibility barrier in the real world. When commuting on the London Underground, for instance, the ambient roaring and screeching of the train tracks can easily hit 85 to 90 decibels, completely masking the quieter nuances of speech or music. To counter this, modern devices employ aggressive real-time dynamic range compression. The DSP continuously monitors the incoming signal and applies a variable gain reduction to the peaks while simultaneously lifting the quietest elements. This squashes the dynamic range, pulling the faint details out of the mud and pushing them safely above the noise floor of the immediate environment. The listener no longer needs to constantly fiddle with the volume rocker on their mobile phone to catch a whispered sentence, as the system maintains a consistently audible and uniform average loudness level. Speech intelligibility does not depend equally across the entire human hearing spectrum, which spans from 20 Hz to 20 kHz. The vast majority of the linguistic information required to distinguish consonants, such as the difference between uncompressed and decompressed or split and fit, resides within a specific frequency band, roughly situated between 1 kHz and 4 kHz. Modern accessibility features leverage this phonetic reality through selective frequency amplification. By isolating this specific speech intelligibility band, the onboard processors can apply targeted gain exclusively to human vocal frequencies. This is particularly beneficial for individuals experiencing mild hearing loss or situational hearing difficulties, such as trying to hold a conversation on a windy street corner. Rather than turning up the overall volume, which would dangerously increase bass and treble levels and accelerate auditory fatigue, the system isolates, sharpens, and elevates the vocal track, ensuring crisp, effortless comprehension. The final pillar of modern auditory accessibility is adaptive equalization. This process relies on a continuous feedback loop between the external world and the internal playback engine. External-facing microphones sample the acoustic profile of the ambient environment hundreds of times per second, identifying specific noise polluters, such as the low-frequency hum of an aircraft cabin, the mid-range chatter of an open-plan office, or the sudden high-frequency clash of traffic. The algorithm analyzes this environmental data and instantly redraws the audio playback curve. If a massive spike in low-frequency ambient noise is detected, the earphone doesn't merely rely on passive isolation or standard phase-inverting active noise cancellation, it dynamically boosts the low to mid frequencies of the actual media playback to prevent the external noise from drowning out the lower registers of the audio track. By constantly reshaping the audio curve on the fly, the device actively alters the original audio mix, deliberately sacrificing artistic purism to ensure absolute legibility, cognitive comfort, and an uncompromised listening experience regardless of the chaos outside. Now that the comments are open on YouTube, I invite you all to share your reactions, ideas, and requests in the section below. Let us keep the conversation going with mutual respect for each other's learning journeys. Keep boosting your English. Bye for now.
Ready to boost your English?